Hi, my name is Katherine Van Kirk, and I'm going today to give you a slightly extended version of the talk that Greg, my collaborator, and I will be giving in Prague on June 26th. This talk is going to be about 40 minutes and is based on the Jacobi factoring circuit, which is joint work from myself, Greg, Seon, and Vinod. I'm at Harvard. I'm in an experimental group. I'm a grad student, and Greg, Seon, and Vinod are all at MIT. And because of the fact that I'm in an experimental group in physics, this talk will not only have a computer science flavor, but also one of quantum physics. So I hope it's a lot of fun. The Jacobi factoring circuit is a super compact circuit for quantum factoring. And normally when we think of quantum circuits, we think of them on a few different axes. We think of both their space, i.e. the number of qubits they require, as well as the depth of the circuit, or the time or the number of layers of gates required to implement it. And crucially, the circuit I'll be talking about today is very, very small and is sublinear in terms of the number of qubits required. And I will get into all of that and why it matters now. So a little bit of background. There are a lot of crypto systems in existence, but RSA is one of the oldest and most widely used crypto systems in existence. And it's based off of the integer factoring problem. So if you have some really large number, say big N, and for RSA, it has two prime factors, P and Q, then the hardness of this problem is what this crypto system is based off of. And in particular for RSA 2048, it is assumed that if you were to write this number big N in binary, it would have 2048 bits. So imagine that my collaborator and I want to communicate, and I want to send the message hi to Seon. I can encrypt this message and send it to him. And when he gets it, he can use his knowledge, for instance, of the factors P and Q in order to decrypt this message and see that I said hi. But now imagine that one of my other collaborators, Greg, is eavesdropping on our communication. He can get access to the encrypted message, but unfortunately, because of the fact that factoring this number is classically intractable, he is not going to know what we said. And this is the key part of the RSA crypto system, which is the integer factoring problem. And the fact that it is really challenging to find the prime factorization of these RSA integers in polynomial time. And the way that the integer factoring problem is posed is in terms of the size, the length of the integer. So here, big N is assumed to have little n number of bits. And this is a convention that I will use for the rest of the talk. But before I get into all of that, I should just give you briefly a quick crash course, if you will, on classical factoring and the algorithms that exist. And I will do so by going into both general integers as well as special form integers. So we could go all the way back and consider, like what is the simplest classical algorithm that we could use for factoring? Well, we could just literally try all of the different integers up to n over 2, big N, and see if they work. And this is the brute force strategy. It is, of course, exponential in little n, and would take a long time. It is certainly not polynomial. The next general factoring algorithm is the quadratic sieve. And there are many works on this. And crucially, you see that the exponent here is going to be square root n rather than n. And this is really nice and came out in the 80s. And then quickly following that, the general NFS came out and is typically considered the best classical algorithm that we have for general factoring. And again, here you see that the exponent is small. It is n to the 1/3, although, this is still a far cry away from poly n. We can now also consider special form integers. So the best algorithm for you to know for the talk today is that of Lenstra's elliptic curve method. And the nice thing about this method is that if you have some factor p of n, and this p is really small, then no matter how big n is, the scaling of this algorithm is only going to depend on the size of the factor. And again, you can see that it depends on the number of bits required to represent p. So this is really nice. And another special form factoring algorithm that I should just mention is that of factoring integers of the form p to the r times q, where r is really, really large. And crucially, when r is big enough, i.e. greater than or equal to the number of bits required to represent p, you can actually factor in polynomial time. And this is really nice. And the reason that I mention this actually is because today we will be talking about integers of the form p squared times q. And so this is a nice algorithm to know, although, crucially here r is going to equal to 2, and so we're not in this regime where you can factor in polynomial time. And if you are interested in learning more about classical factoring algorithms, I recommend this survey, A Tale of Two Sieves, from Pomerantz. So all of this is classical, and you can wonder, what happens when you actually have access to a quantum computer. And let's say that my collaborator, Greg, teams up with my group members at Harvard, where they build neutral atom quantum computers in the Lucan group, and they team up together. And Greg saves the message that I sent to Seon. And one day when we have a neutral atom quantum computer that's big enough, we can imagine factoring this RSA integer, and then Greg will be able to see what I was saying to Seon. And you might wonder, like, okay, when is this going to happen? There are a ton of works, resource estimation papers that have come out, especially recently. This one appeared in May of 2025 from Craig Gidney. And these resource estimation papers are quantifying, how many resources are going to be needed to actually factor, for example, RSA 2048. And while I'm not going to get into the details of this, I do just want to flash up Craig Gidney's conclusion because I feel like it is a really nice summary of where the field is at right now. And the point that I want you to draw your attention to is that he does not know, given all of the research that has been deployed up until, of course, May of 2025, how to factor a 2048 RSA integer with only 100,000 noisy qubits. And this is really, really interesting because it means that, classically hard factoring is a certain distance away. But that being said, he does quote the crypto saying that attacks always get better. And so it is possible that we can see something that reduces this. And, also to his point, over the past decade that have been really incredible attacks for quantum factoring. And this is really getting into the meat of what I'll be telling you about today, which is this new era of quantum factoring and the fact that we have seen incredible asymptotic improvements to factoring over the last 2 years, even though Shor's algorithm for quantum factoring has been around for the last 30 years. So, Shor's algorithm, like I just said, has been around for 30 years, and many people have worked on improving it in terms of a lot of constant factor improvements. I put Craig Gidney here because he's done a lot of really amazing work. But 2 years ago, Oded Regev came out with a new quantum algorithm that is basically just a multidimensional analog of Shor's algorithm with some really nice, clever arithmetic subroutines to reduce the modular exponentiation costs. For experts, that will mean something. Don't worry if not. And the point of Regev's algorithm is that he was able to dramatically reduce the depth required and the gates required for running Shor's algorithm. And Seon and Vinod came along and were able to also reduce the space to be on the same order as that of Shor's original algorithm. But, both of these quantum factoring algorithms are for general integers. And so, any number n that you want to factor, you can. But you can also consider special form integers. And like I mentioned earlier, you can consider the integers p squared times q. And in 2012, Li, Peng, Du, and Suter actually proposed a quantum circuit that addressed this special purpose problem. And what we have done is we have dramatically reduced the space and depth of this circuit. And that is what I'm going to be focusing on today. And I can just toss up the asymptotics because I feel like the asymptotics tell the story really well. So first, of course, we want to set the stage by considering the asymptotics required of Shor and Regev's algorithm using the improvements from my collaborators. And you see that the gates and qubit counts are as follows. And I should say that this is using fast integer multiplication. All of these quantum algorithms have underneath them, some number of multiplications. And so the multiplication algorithm you use is going to inform what the asymptotics look like. And so that's what's here. And another algorithm that we should just contextualize with is that of x squared mod n. This is a interactive proof of quantumness, and this is work from my collaborator Greg in collaboration with Soonwon Choi's Umesh Vazirani and Norman Yao, and came out in 2021. And the really nice thing about their work is that they were able to propose a algorithm based on the hardness of factoring that has very few gates, and the cubic count is the same. But the key thing to keep in the back of your mind is that this, while it's based on the hardness of factoring, it's not actually factoring. And then the other algorithms that we should consider here are finally that of our special form factoring p squared times q. And first I have the result of the LPDS team, which, like I said, came out in 2012. And then I have our result. And what I want you to really notice is that of the space. Here, our space is in terms of little m, which is the size of the factor q, whereas all of these other protocols are going to be in terms of little n, where little n, like I said earlier, is the number of bits required to represent the composite number big N. And so crucially, if we have a factor q that is substantially smaller, then we get sublinear scaling in terms of the space. And that's actually what is going to happen. We are going to see that classically factoring, when we have m on the order of little n to the 2/3, is going to be classically hard. And like I said earlier, all of this is based on fast integer multiplication, and this is the cost. So with that, what I'm going to talk about today is I will give you a high-level overview of our new factoring algorithm, its implications, and I will do so by first really honing in on Shor's algorithm and explaining what's happening so that we can then really deeply jump into and understand the meat of our Jacobi factoring algorithm. So let's start with Shor's. As we know, the goal is to find a prime factor of the number big N. And here I'm just going to assume that we have two prime factors, P and Q. Although, like I said earlier, this can be a general factoring algorithm. And what Peter Shor did in the 1990s was he was looking at this function, and this function is periodic with period P. And actually, before I tell you what he did, let me just make a comment about this function. The fact that it's periodic with period P means that if you were to input some input x and then you were to add P to it, that you would just get back the same value f of x. And we can actually visualize this. So we can visualize this with a number line. Here I'm representing all the different possible inputs x as different points on this number line. So each dot here is a different integer. We go 0, 1, 2, 3, so on and so forth. And crucially, because of the fact that this function is periodic, if we consider the color of each point to denote the value of the function at that point, then if we were to choose some point on this line and add the period to it, then we should get back the same color. And we see that that's actually exactly what is happening here in this depiction. So we have this sequence of colors of black, yellow, pink, blue, green, and then back to black again. And the sequence of colors after the period P is going to repeat over and over and over and over again over the course of the number line. And so this is just a visual representation of what's happening, and we're going to use this visual to better understand Shor's factoring algorithm and later the Jacobi algorithm. Okay, so what did Shor do? So Shor came up with a quantum subroutine for finding this period, and then crucially, he was able to find this quantum algorithm because this quantum algorithm, once you have the period P, you can use the period to come up with a good guess for one of the factors P or Q, big P or big Q. And like I said, this period finding subroutine is what you're actually going to do on your quantum computer. And the process of coming up with a good guess afterwards, I'm actually not going to talk about. It's very simple. And it always is going to give you a good guess with some constant probability. So if you don't get a good guess on the first time, then you can just do it again. Okay, so what does the quantum subroutine look like? First, we are going to create a equal superposition over all the points in the number line up to 2 to the little n. And the way that you do this is by creating the all zero state in your quantum computer. That's how you initialize. And then you're going to apply a Hadamard to every single site. And that creates a superposition over all bit strings, i.e. a superposition over all the different points in the number line. Here, each bit string is going to identify a different point. Then in superposition, you are going to, in a newly introduced register, compute the value f of x of this function. And again, the value of this function corresponds to some color. And so, some point x on this number line is going to have some associated color, which is the value of this function. Then what you're going to do is you're going to measure the second register. And because here the value of the function is represented by a color, you can imagine that when you measure, you are just given a color. Imagine that you're given yellow. And using the principles of quantum mechanics, that projects your first register to be in an equal superposition over all of the different points that corresponded to that color. Here, because of the fact that we chose yellow, it's going to be a superposition over all the different points on the number line that give a yellow value of f of x. Then we're going to do the Fourier transform of this, and that just translates this like train of delta functions into a new train of delta functions with a reciprocal period. This is just a common fact of the generic Fourier transform, and the quantum Fourier transform is literally just the quantum version of it. So all of your normal signal processing stuff holds. And then finally, you are going to measure. And when you measure, you're going to get some random multiple of 1 over p. And at this point, you can just do continued fractions and get out the value of your period p. So great. So like at a high level, what has happened here is we use the periodicity of this function to, along with, this measurement step in step 3, to get out a periodic signal, which then allows us to extract the period. And this is crucial and will help us understand the Jacobi factoring algorithm. And before I get into the different details, I'm just going to give you the high level by going back to Shor's algorithm and juxtaposing Shor's algorithm with that of the Jacobi algorithm. So this second step that I have highlighted on this slide is the kind of like key subroutine of the factoring algorithm, because this part is going to be the most expensive step of all the ones that I've listed here. And so you might ask, well, Katherine, what if we could find a new periodic function where the period would still give you information about the factor, but would be more simple or easier to implement than this function f of x? And that is actually exactly what is going to happen in the Jacobi factoring algorithm, where we're going to propose some new function, j of x, that is going to factor numbers of the form p squared times q. And crucially, this function is going to be periodic, but instead of being periodic in just some period p that gives you a good guess, it's going to be periodic directly in the factor q. And what that means is that as soon as you do your quantum subroutine and you get out the period of the function, you don't have to do any of this guesswork after the fact. You get the period, and the period is one of your factors. And you might be wondering, okay, we had this really nice visualization of what Shor's factoring algorithm looked like, and can we do something similar for the Jacobi factoring algorithm? And the answer is yes, and this is what it looks like. So the Jacobi factoring algorithm, the function that is underlying it is that of the Jacobi symbol. And the Jacobi symbol, crucially, is going to be periodic in the factor q. And the Jacobi symbol, for all intents and purposes, takes on only 2 values, -1 and +1. And so you can see that, if we again pose this as a number line where the color corresponds to the value of the function, then we are only going to have 2 colors here. Here I've just chosen yellow and a dark blue. And you might be looking at this and wondering, okay, like something that's a little bit weird about this is that you don't have this like sequence of colors that is then repeated over and over again. Does this mess up your periodic structure? And the best intuitive analog I can give you is that of a barcode. So if you take a barcode, which is some random sequence of white and black lines, and it has some length, and you take your barcode and you repeat it over and over and over again, if you kind of sit back and squint at it, you do see that a periodic structure emerges. And so it's not like crazy to think that, you can actually extract the period, i.e. the length of this barcode, from a period finding algorithm. And that is just exactly what happens. And the key detail is that what is actually happening within a single barcode or within a single period with these dark blue and yellow dots is truly random. Like the sequence there is truly random, which allows us to get then composite information about the period Q when we do our period finding quantum algorithm. Our period quantum finding algorithm is going to look very similar to that of the period finding subroutine of Shor's. The only difference being that we now have this new function, j of x, that we are computing in superposition as opposed to the old one. And the third step is going to be the same, where we take a measurement of the second register. And what that does is that projects you into a superposition of many different shifted functions of the period Q. And again, you take the Hohn Fourier transform and you have this series of delta functions again with this reciprocal 1 over Q period. And again, you just get the outcome, which is some integer multiple of 1 over Q, and you can do post-processing to get out the factor Q. And all of this that I've given you so far is content that was in the really nice work of Li, Peng, Du, and Suter in 2012. And, all this is to say, the key idea of what we are proposing in this context is that we can actually reduce the size of this quantum algorithm using the fact that this period is going to be Q. And so we can actually bound the space complexity in terms of Q rather than N. And let me just break down for you what this means. So again, we can go back to this number line picture and we can just notice a few things about it. The first thing that we can notice is that we only have two colors. And the thing that is actually representing what color we have here is this second register, the one that holds j of x. But because j of x is only going to be +1 or -1, what that means is that you basically only need a single qubit to actually represent the value of the second register. So that's great. And so unlike Shor's, where you need on the order of little n qubits for the second register, now you just need basically one, which is great. And now the next thing that we can notice is that this superposition is going to extend not actually as far as it needs to extend in Shor's algorithm. In Shor's algorithm, because the period can be on the order of the number that you're factoring, you have to extend your superposition to be really far in order to get enough information for your quantum Fourier transform to give you something meaningful. Here, on the other hand, you don't actually need that because of the fact that your period is the size of your factor Q. The superposition doesn't actually have to extend as far in order for you to get good information from your quantum Fourier transform. Okay, so with that, I will go into the Jacobi symbol. So the Jacobi symbol can be best understood when we consider a ring, mod Q, where Q here is assumed to be prime. And we can just choose some point on the ring and call that the 0 point. We then go to the 1 point, the 2 point, and so on and so forth, and we can label all the points on this ring up to Q minus 1. So this represents X mod Q. Now imagine squaring all of these inputs. And we can see, when we square these inputs mod Q, what points they land on. If you square 0, you get back to 0. If you square 1, you get back to 1. If you square 2, you hit 4. If you square 9, or if you square 3, you hit 9. If you square 4, you hit 16, and so on and so forth. And if you keep going around and increasing x and squaring x and seeing where you land, it turns out that you'll only actually ever hit half of the points on the ring. And so what you have here is you have a flag for whether or not a point is a quadratic residue. Yellow if it is a quadratic residue, i.e. that's when it was lit up, and dark blue if it is not a quadratic residue. And that's exactly actually what the Jacobi symbol is. Here's a more formal definition where the Jacobi symbol is going to be +1 if, your input A has a some x on the original ring where when you square it, it's congruent to A mod Q. But it is going to be -1 if it is not a quadratic residue, i.e. if there is no x such that when you square it, it's congruent to A mod Q. And then I should just note that, in this definition, I say that it's as long as it's a non-zero quadratic residue. It turns out actually the Jacobi symbol takes on three values, +1, -1, and 0, but the 0 value basically doesn't appear. And when it does appear, it doesn't make a difference. So for your understanding for now, don't worry about it. This is the key high-level point. Okay, so here I have included all the information that you need to know about the Jacobi symbol, and we can now ask the question, how do we use it for factoring? Well, the Jacobi symbol that we compute in our factoring algorithm is with respect to the big number n, but we just define the Jacobi symbol with respect to prime q. And crucially, n is not prime, we're trying to factor it. So Rn takes the form p squared q, and the Jacobi symbol has the property that it actually factors into the Jacobi symbol with respect to its prime components. And because of the fact that the Jacobi symbol just takes on the values +1 and -1, no matter what the Jacobi symbol of x with respect to p is, you're just going to get back the Jacobi symbol of x mod q because of the fact that these two x mod p Jacobi symbols will cancel. And so crucially, this is actually the barcode. And so if we look at what our factoring algorithm looks like, we are computing the Jacobi symbol with this, which is the Jacobi symbol of x with respect to n, but it's really just underneath the hood, giving you the Jacobi symbol with respect to q. And so that is the thing that is being repeated over and over and over again, is this sequence of yellow and blue dots from the ring that we talked about earlier, where the length of the sequence is going to be q. And that is why we have a function that is periodic with period q. And again, crucially, like what is actually happening within one period q, all the different points are completely random, and that is a guarantee that helps you know that what you get out of your quantum subroutine is going to be one of the factors q. Okay, so now let's discuss the algorithm to compute the Jacobi symbol. And crucially, we've discussed why this key idea for why we can bound the space to be in terms of the size of Q. But this one piece that we didn't discuss is that the Jacobi symbol is with respect to n. So one of the inputs of our quantum algorithm is going to be big N. But big N is represented with little n space. And so, you might ask, how can we compute the Jacobi symbol when one of the inputs requires little n space, when we actually only want to only ever use little m space? So the way that this is going to happen is going to be using a binary GCD-like algorithm. So the Jacobi symbol can be computed using its properties of swap and mod. And just like you see in the binary GCD, we can construct a recursive algorithm where, the size of A relative to B decides which property we use. And you'll see that if you actually employ this, I'm having an example problem over here on the right, where the little, the bottom number is big N, and the top number is X. You're going to see that, when you first apply this algorithm, that the bottom is going to be much bigger than the top. And so you're going to swap, and then you're going to take mod, you're going to swap again, you're going to mod again, and you just continue this on and on and on until you eventually get your +1 or -1 value for the Jacobi symbol. And this is like how you would compute the Jacobi symbol classically. The quantum version would be exactly the same. And when you do this quantumly, you can make a couple observations. So first, the bottom number is always going to be bigger than the top number at the very first step. And so as a result, what you're going to want to do is you're always going to want to do a swap and then compute n mod x. And then after that, the rest of the computation is literally just going to be space corresponding to little m, because of the fact that you just took big N with respect to mod little x. And so this bounds the space of the remainder of the computation. And crucially, the only step here that really requires space more than little m is going to be this first step where you're computing n mod x. And so the question for whether we can compute the Jacobi symbol with space little m is really, can we compute n mod x in space little m? And I'm going to give you the key idea here. And I'm going to spec it out for you by expressing x and n with just two example bit strings. And, again, the question here is, how do we compute n mod x when one of the inputs is going to be size on, right? Because again, the way that we want to compute this is with space little m. And the key idea is that we're actually going to chunk up our input n into pieces that are size little m. And then our solution is going to be streaming these small chunks of our number, big N, into our quantum computer. So we can just briefly look at what this would be like in practice. So we have a classical computer that controls our quantum computer. And our classical computer is going to feed little m bits of n at a time to the quantum computer. So, it'll first take the lowest order bits. That's a detail that we discuss in our paper, which I'm going to leave as a detail for now. And we feed these bits into our quantum computer, and we do some arithmetic. Underlying this is a few different arithmetic operations, one of which is multiplication. But the point is that you do some arithmetic, and you're going to wait as you do this computation until you have little m qubits free again, at which point you can then send in the next piece of n, and then wait again while you do your arithmetic, and then send in the next one, and then the next one, and so on and so forth until you have sent all of your number big N into your quantum computer. And so while you were actually able at the end of the day to process little n bits of information, your quantum computer at any given point in time only needed little m bits of space. So, this question of can we actually compute the Jacobi symbol with little m space? Yes, we do so via streaming. And the streaming approach, while we didn't get into all the details, already gives us a sense of what the space-time complexity is. So, we can just look at this and already enumerate the gates, depth, and space. So the number of streaming steps that we have is going to be little n divided by little m. And for the gates and the depth, then the cost is just going to be the number of steps times the cost per step. And the space is just going to be the space required for any one of the steps. And when we sub in the cost of fast integer multiplication, these are the different values that we get. And then finally, you can remember that after this first initial step of computing n mod x using this binary GCD-like approach, we then had to do the rest of the Jacobi computation. And therefore, you just need to add on this extra factor of little m for the depth. So with that, that is a very high-level view of our Jacobi factoring algorithm, and I can now conclude with some high-level takeaways and open questions. So our main result is a new quantum circuit for factoring integers of the form p squared times q. And crucially, it is hard to classically factor these integers when the factor q needs n to the 2/3 bits to be represented. And the reason that we have this n to the 2/3 is because this is where Lenstra's ECM is equal to the NFS in terms of the classical complexity. And so we set these two equal to each other, and that gives us n to the 2/3. And when we compare this quantum algorithm to other quantum algorithms for classically hard factoring, we see that this algorithm has the lowest space complexity, and like I said earlier, is in fact sublinear in the number of qubits needed. And therefore, when we do a first demonstration of quantum factoring in the lab, this is actually likely how we should do it. So with that, Our algorithm lets you solve for Q. There's actually a crypto system based on P squared times Q, even though it's not quite as widely used. And in fact, our algorithm can be generalized to factor any n of the form that I've written below, where you have a bunch of different prime factors with distinct exponents. Um, we can pose some open questions. The first one, which is kind of the most natural, is what are the concrete costs of these algorithms? And this is ongoing work from our same team. And next, there are a lot of really cool co-designed algorithms coming out, co-designed with quantum error correcting codes. And it would be really cool if someone could co-design a gadget for computing the Jacobi symbol with, say, um, a quantum LTPC code. That would be great. Um, Another question is, are there better classical algorithms that don't exist yet for computing p squared times q when q is small? And, can you take advantage of structure like we did in our quantum algorithm? And then finally, there's a really broad landscape of algorithms in the classical world where, when you have special form integers, you can more efficiently factor. And in the quantum factoring landscape, there really hasn't been as much of a landscape exploiting structure in N. And so it'd be really cool to see more quantum algorithms that actually exploit special structure. Finally, I would like to conclude by saying that the combination of our result of a very compact quantum first circuit for classically hard factoring with the emergence of early fault-tolerant digital hardware, I think actually brings quantum factoring a lot closer than previously thought. This diagram here is a diagram from my group where we do neutral atom quantum computing, and it'll be really cool to see over the next few years what the combination of these results can bring. So thank you so much. And thank you to my wonderful collaborators. They're truly a joy, and I can't say enough positive things. Here's the archive link. And again, thank you.